الصلاة والسلام على محمد. وعلى الطاهرين. السلام عليكم ورحمة الله. طاعتكم مع الله إن شاء الله. مسيس دلال، مسيس دنام، مسيس سبا. أهلا وسهلا. إن شاء الله طاعتكم مقبولة. صيامكم اليوم. سلام ورحمة الله. Okay. I finished the first part of the lecture. The first part was about transformations. Okay. The first part contained discrete Fourier transform, discrete cosine transform, transformation. Okay, discrete Fourier transform, discrete cosine transform, discrete Hadamard transform, discrete Walsh transform, KLT. Okay, and these transforms. We are entering the second part of the lecture, image enhancement. Okay, image enhancement, and this time in this session we have a review over this topic. That's right. We start. Digital image processing, image enhancement. Review of spatial domain methods. We had two domains: a spatial domain and frequency domain, or a spectral domain. Spatial domain is X or Y domain. A spectral domain or frequency domain is, for example, UOV domain. Okay, the original domain is a spatial domain, and we see some methods in a spatial domain this time. A spatial domain for enhancing the quality of image. The goal of image enhancement is to process an image so that the resulting image is more suitable than the original image for a specific application. For example, for image edge detection. Okay, for some items, for some specific application. We enhance some features of our image. That's right. Of better quality in terms of some quantitative metrics. Okay. In each situation, it maybe differs. Some how metrics, and visually better for vision by, for example, RA. Salam, Mrs. Zainab. Salam, Alam Salam. Image enhancement method classification. We have two domains for enhancing. Okay, spatial domain methods and spectral or frequency domain methods. Okay, this time we only see spatial domain methods for enhancing an image. This session we are focusing on only a spatial domain. We said review of a spatial domain methods this time. Okay, this session for image enhancement. That's right. Special domain methods, local neighboring method processing or local neighborhood processing. Okay, neighboring of some pixel. Okay, a pixel in x or y, a special x or y, neighborhood of it. Okay, a neighborhood around each pixel x or y is defined by using mainly a square, okay, or rectangular image patch centered at x or y. This item. This is x or y, and this is a rectangular around of it. Okay, a patch around of it. This is a neighborhood. An operator, for example, T transform. Salam, Mr. Hamid. Salam, ahlan wa salam. طاقتكم مقبولة. An operator T or Tx or fx or y is defined which manipulates all pixels within the specified neighborhood mentioned above. Okay, this rectangular centered at x or y, this item, and produces a single response. For example, gx. City. Excuse me, my connection was cut. Do you hear me this time? Okay, that's right. We said a very important family of transformations of that type are so-called gray level transformations or intensity transformations. Okay, of the form S is a transform of R. Okay, this R is an intensity level, and this S is the new intensity level for example, some pixels. Okay, for some x or y pixels. That's right. R or S are the gray levels or intensity levels of F and G at, for example, a point of x or y. That's right. Observe that the transformation of a pixel depends on its gray level only and not its coordinates or x or y. We see to intensity, not to its location. Okay, it's right, left, top, down, etc. We only see the intensity. For example, we see in the next slides. For example, for low intensity levels, we higher it. For example, for high intensity levels, we lower it, etc. That's right. These techniques are called point processing techniques. Okay, each point, the gray level of each point is, for example, degraded or enhanced. To name a few, this is the names: constant manipulation, handling the contrasts of an image. Okay, or enhancing, enhancement, stretching, threshold. These are the names. Or image negatives, or log transformations. These transforms, all of these are point processing, okay? Or power log transformations. We see all of these or most of these items in the next slides, okay? Or gray level slicing, or bit plane slicing, or histogram processing and processing, etc. That's right. Go to the next slide. For example, the first one is in the domain of point processing, okay? In spatial processing or spatial enhancement, in the field of point processing, the first one in this slide, we have contrast manipulation, okay? Or enhancing or differing the contrast of contrast of an image. In the figure below, here, we see here abruptly changing the contrast. Okay, this the horizontal axis is the intensity, the input intensities. Okay, this is R. For example, this is the lower intensity or zero intensity, and this is the higher intensity. Okay, or for example 2055. These items, for these items, the output intensity is dark or is zero. Okay, from this time abruptly, for example half, okay, we see that intensity is high or is light, or for example is 255. This is abrupt, this is sharp, but this is a smooth. Okay, lower intensities for input, lower intensity for output. Okay, higher intensity for input, higher intensities for output, or higher gray levels for output, but changing not very sharp, but some sharp. Okay, not very sharp. For example, some linear. That's right. In the figures below, you can see examples of two different intensity transformations which aim at altering or alternating the contrast of an image. The figure on the right, this item, sharp, shows the process of binarization, okay, of the image. Low, high, a fixed threshold before it, low or okay. For example, this is 0 0, this is full, or for example LL, okay, L, this is the maximum of intensity level. Okay, and this is one point and this is another point. You can, for example, stretch this line, this point to, for example, below, okay, or pull this point to up. That's right, and change the rate of this line, and these lines. Okay. Okay, another type of transformation is a piecewise linear, not totally linear. Okay, this item, this is linear. This is linear. Okay, this is, for example, this is linear. But for example, this, this is piecewise linear. Okay, piecewise linear. In each sections we have some slopes. Okay, this is a slope of 1, a slope of 2, a slope 3. That's right. Okay, I delete this item. Okay. Another type of transformation is a piecewise linear function, shown below, depending on the slope of each straight line. This S1, slope 2, slope 3. Okay. Depending on each slope, the original local range of intensities or grade levels is decreased when a slope is smaller than 1, or increased when a slope is more than 1. Okay. Intensity, a slope is small, intensity is decreased. A slope is high, intensity is increased. Okay. The locations of R1 or S1, this point, and R2, S2, this point, control the shape of the transformation function. Okay, changing these points, you can change this slope and this slope and this slope. That's right. For example, if R1 is S1 and R2 is S2, okay, the transformation is a linear function, not piecewise linear, real linear, as this item. This is a linear transformation. Okay. For example, this is R1 S1 and this is R2 S2. Okay. P1, P2, and a linear function produces no changes. Okay, because this slope is 1. This slope is 1. Each input, this is R and this is S. Each input grade level is transformed to the output grade levels without any changing. That's right. But for example, if R1 is R2, R1 is R2, this is the same as this. That means this item, 1 point, okay, not 2 point, for X, for horizontal level. And S1 is 0 and S2 is the maximum. Okay, this is R1 is R2, S1 is 0 and S2 is the maximum. Okay, L minus 1. The transformation becomes a thresholding function that creates a binary image, this item. Okay, in the last slide, this item. That means changing these 2 points, you can change all and create all functions. Okay, Salam. Excuse me. Problem was from my side. Salam, Mr. Ali Zubaydi. Excuse me. That's right. Go here, and we said this was the original image. Okay. Shukran. This was the transferred image by using this transfer function, and this is the transferred image by using a binary transformation. Okay, that's right. Another one for point processing, image negatives. Okay, for example, in medical images you have see, for example, X-ray images, okay, or CT images in the hospitals using image negatives. Then this is the transfer function. Again, this is R, the original image gray level, and this is S, the new or transferred gray level, okay, or intensity level. This is, for example, when the input is in dark situation, the output is in bright, full bright, okay, and when the input is in full bright, the output is in full dark, okay, completely negative. That's right. The negative of an image with intensity R in this domain, for example, from 0 to L, okay, from 0 to L minus 1, is obtained by using the transformation function S is L minus 1 minus R. Okay, for example, 0 is transferred to 255. 255 is transferred to 0. Okay, 255 minus 255 is 0. 255 minus 0 is 255. Okay, completely inverting. The above function reverses the order of gray shades from black to white, okay, or bright, so that dark to bright, so that the intensity of the output image decreases as the intensity of the input image increases, okay, dark to bright and vice versa, بالعكس. These images are used mainly in medical imaging science, okay, in X-rays, in CTs, etc. For example, here, from a patient, okay, observe that in mammography, okay, an image for this is the original image from a mammography, and this is the resultant. Observe that the suspicious region in this item, okay, the suspicious region is highlighted better in the negative image here, okay, this is better seen. That's right. A original digital mammography image, okay, or mammogram, and B negative image obtained using the negative transformation. That's right. Okay, go to the next slide. This is image negative or negativating. Another technology or technique in point processing, okay, for spatial image enhancement. This is log or logarithmic transformations, okay. And the log transformations are a family of transforms of the form S is C log 1 plus by R. We had it in the last sessions, okay, in part 1. And C is a constant. They are used. This is the figure for logarithmic, okay. This is they are used to enhance the range of small intensities which is compressed. Small intensities are compressed, okay, and therefore not visible. Small intensities are not visible. Why? Because they are compressed in gray level, okay, in images with large range of intensities. For example, this log is for differing or for varying the dynamic range, okay, for enhancing the dynamic range of gray levels. That's right. This is the original image, okay, not a very information in it, okay, and this is the resultant image. We see more information, okay. Here Fourier spectrum. We had this Fourier spectrum in the last sessions, okay, in the DFT session in part 1. In DFT section in part 1. This is the Fourier spectrum, okay, but not visible and not more information. But this item is B, result of applying the log transformation given in this equation, okay. This is more better than this one, okay. This is log transformation. Another transformation in point processing. Another transformation is power law transformation. Power law transformation. This item, this figure, plus of or here, the power law transformations is a family of transforms of the form S. The transformed level S is C dot R powered by gamma. R is the input gear level and S is the output gear level. C is constant, normally 1, okay. R powered by gamma. C and gamma are constants. This technique is often called gamma correction, okay, and mainly used in monitor displays. You almostly used these items, okay, in your display, gamma correction, or for example in Photoshop, in Corel, okay, you mostly used it, gamma correction. But this item, you see, this is the R and this is the S, okay, gear levels. You see that these items, for example, this is for small gamma and this is for large gammas, okay, and this is this line, this is the linear, no change is by gamma is 1, okay. That means if C is 1 C is 1, R powered by 1, okay? S is R, S is R, this is the linear, no change, okay? But, for example, if gamma is 0, R powered by 0 is 1, okay? Each number powered by 0 is 1. C is 1, S is 1, okay? This is, if gamma is 0, S is 1, this item. Full range, that means full range, okay? And increasing gamma, you change to this item, okay? This item. That means when gamma is increased, R is very important. R is very important. Large R's tends to large S's, okay? And small R's tends to small S's, okay? That's right. Go to the next slide. Here, for example, you see an original image, but when transferred to CRT or display, the quality is bad, okay? Because of this gamma function of this CRT itself or display itself. But we use this, the inverse of this gamma function of display, this, and the resultant shown in the display is better or good or as the original image, okay? You see here a linear wedge grayscale image, okay? This is an linear wedge constructed image for original image. B, this response of monitor to linear wedge, response of monitor to this input image. You see this is bad, okay? This item is even more darker than this one, and okay, because of this gamma function of the display itself. But using this inverse gamma function to the original, okay, and this should be shown over the display, and this is the resultant over the display. You see this item is near to this item, okay? C, gamma corrected wedge, this item, and D, output of monitor. Output of monitor is the same as original image. Okay, go to the next slide. Another example of power law transform. This is the original image, okay, from the sky, and these items are the corrected images with some gammas, okay? For example, here you see this is with gamma 3, this is with gamma 4, and this is with gamma 5, okay? You see more gammas, more contrasts, okay? Here, aerial image from the sky, and all of these items, B to D, resulting of this transform, power law transform with C is 1 and gamma 3, 4, 5. That's right. Which is better depending on our case, okay? Maybe this is better, maybe this is better, and maybe this is better, or maybe this is better in our case. But you see that with increasing the gamma, you choose, reach to a better contrast, okay, or more contrast. This is less contrast, and this is more contrast, and these are moderate contrasts. This is gamma 0, gamma 3, gamma 4, and gamma 5. Go to the next slide. Another technique in point processing, okay? We are in a spatial a special gray level enhancement, and we are in point processing. And in point processing, we are here in gray level slicing. Gray level slicing. You see this item, for example, and this item, for example. You see this is the input gray level, okay, R, and this is the output gray level, okay. You can change only these items. For example, gray levels between A and B. Gray levels between A and B has gone to a brighter, more brighter gray level, okay, or more intensity. All other levels are the same or unchanged, okay. In this time, all of the unchanged. These are changed, okay. Between A and B, we have more brightness, and between these items we have more darkness, okay. Fixed darkness, darker and brighter, but fixed, okay. All of these items have a fixed gray level, and these items between A and B, input of A and B, have a fixed but brighter. But this item, this item between A and B, no, all other items, we have a linear transform, okay. That means the input gray level has transformed with no change to output gray level, okay. But in this item, gray levels between A and B, we have more brightness, okay, than this one. More brightness, brighter, but fixed, okay. We read here. The goal is to in gray level slicing, the goal is to highlight a specific range. A specific range means between A and B, okay. Highlight a specific range of gray levels in an image, for example, to enhance certain features, okay. In each case, one way is to display a high value for all gray levels in the range of interest. This item between A and B, high value or brighter, okay, and a low value for all other gray levels, okay, a low value, darker for others outside of A to B range, okay. And this means binary function, okay, in transforms, binary transform or a binary image. But this one, the second approach, is to brighten this item, to brighten the desired range between A and B, okay, this item of gray levels, but preserve or not change or no change the background and gray level tonalities in the image. All other ranges, okay, all other ranges are unchanged, this item, this and this, but between gray level of A and gray level of B, this item, we have more brightness, okay, but fixed. This is the second approach in gray level slicing. Gray level slicing. Go to the next slide. For example, some examples. This example is for this item. This transformation highlights range A or B of gray levels and reduces all others to a constant level. Okay, but not this item. No. A, B, C. This is A. This is A. This transformation highlights range A or B. This item highlights, okay. More gray level. This item is highlight. And reduces all others to a constant level. These items, these and these, okay. The A as previous slide. B, this transformation highlights range A or B. This highlighting range A or B, more S, okay, but preserves or not change all other levels. These items are linear, okay, linear, no change. C, C, this is the original image, okay, an image. D, result of using the transformation in A, okay, not for example, not example for B, in A. You see, for example, some levels of pixels are highlighted. For example, these are neglected or ignored, and these are ignored in the resultant. That's right. But for example, here is better chosen. Okay. These and these are ignored. These transformations aren't spatially, okay, not for X or Y, are for gray level, for intensity level, okay. Thus, this item and this item, both of them are deleted, okay, and changed to a darker area, okay. That's right. Go to the next slide. Another technique in point processing, in a spatial enhancement, okay. We are in this session, we are in a spatial image enhancement, and in this slide, we are in point processing, and this slide in bit plane slicing, okay. Excuse me. Another technique named bit plane. The goal is to highlight the contribution made to the image's appearance by specific bits. Assuming that each pixel is represented by 8 bits, okay, the image is composed of 8 1-bit planes, okay. I show the next slide. This is the next slide, okay. This is the first plane, second plane, third plane, etc. This is this plane is for bit 0, bit plane 0, or less significant bit in all other the X or Y's, okay. This plane is for bit 1. This is for bit 2, etc. This is for LSB and this is for MSB, okay? Mass square bit 7, for example, and all other X or Y's, okay? All other in a spatial of the image. That's right. Go back. Assuming that each pixel is represented by 8 bits, okay, the image is composed of 8 1-bit planes, okay. We saw each plane, LSB plane and MSB plane, and between them. Plane 0 contains the least significant bit, and plane 7 contains the most significant bit, okay. Only the higher order bits, bit 7, bit 6, and bit 5, for example, okay. Only the higher order bits, or for example top 4 planes, okay, the half of high half, contains visually significant data, okay. You know that bit 7 is more significant, okay. Bit 6 is after it, and 2 bit 0, okay. The other bit planes, for example, bit 0, bit 1 in these items, the other planes contribute the more subtle details, okay? Not most significant, less significant, okay? Or for example, for tuning, for tuning, or for least qualities, okay? In Persian and in Arabic we say latafat, latif, zarif, okay? Subtle means in these items. That's right. Plane 0 with plane 7 corresponds exactly to an image threshold at gray level 128, okay? Most significant. This is slide. Plane 0 bit 0 and plane 7 bit with bit 7, okay? Here, for example, this is an input image, okay? This is an input image. For example, an 8-bit fractal image. What's fractal image? A fractal is an image generated from a mathematical expression, okay? From a formula. You know what's a fractal. This is a nice image, okay? A nice image and a fractal. This is the original image. But go to the next slide. You see, you see here the 8-bit planes of the image in previous figure, okay? The number at the bottom, for example, 7, 6, from here 0, 1, 2, 3, 2, 7, okay? The number at the bottom right of each image identifies the bit plane. You see that this is bit plane 0 with bit 0, okay? No information, no mass information, but this is containing very information, okay? Most information is here. After it, this information. This is bit plane 7, most bit plane, most significant, okay? MSB, most significant bit. This is after it and this is after it. Only using these 4 images. These 4 images is, for example, more than 19% of your information in the original image, okay? Original image. Or using, for example, only these 2 images. Only these 2 images. You have, for example, most section of the information. That's right. This is bit plane slicing. And go to the and the last slide. The last slide for this time for a special image enhancement. Image enhancement in the spatial domain. Summary of intensity or gray level transformations. Okay, all of for example, last slides are gathered in this slide. Okay, that's right. Some basic gray level transformation functions used for image enhancement in a spatial domain. Linear, negative, identity, logarithmic, log, inverse log, power law, nth power, and nth root. Here you see the horizon is the input gray levels, okay, from dark to bright, okay, full brightness, and this is the output gray levels, okay, or output intensities. For example, this item, this line is the identity line, okay, that means no change. Each R transformed to is equal S, okay, S is R, no change. This item, for example, this item is negative, okay, full dark transfer to full bright, okay. Full bright in input image is transformed to full dark, okay, etc. This is negative. And for example, this is log as gamma, okay. Log is as the gamma transform. This is log. This is inverse log, okay, as another gamma. Log is as gamma, small gammas, okay, in gamma transformation or gamma correction, and inverse log is as more gammas or large gammas, okay. But this is nth power, okay. For example, power of 3, power of 4, power of 5, and this is inverse of power, okay, or nth roots. For example, second roots, third roots, okay. That's right. This is the complex of spatial domain enhancement, okay. In this time we had image enhancement in only a spatial domain. In the next session, inshallah, we go for histogram. Firstly, inshallah, histogram, and after it go to some filters in the spectral or frequency domain. That's right. Each of you, I name your name and please type 1. And Mr. Abbas, are you ready in the class? Please type 1. Mr. Abbas. Mr. Abbas, do you hear me? Mr. Ahmed Qasem, please type 1. This is Huzur or Ghiyab. Mr. Ahmed Qasem, do you hear me? Mr. Ali Az-Zubaydi. Mr. Ali Az-Zubaydi. Mrs. Dalal. أحسنت. شكرا. Mrs. Dana, are you ready? أحسنت. Okay. I know, Mrs. Dalal. Mrs. Lom'e. Mrs. Lom'e, are you ready? أحسنت. Are you ready means حاضرید. Mrs. Dalal said حاضرم. حاضرم means أنا حاضرم. أنتم حاضر or أنت حاضر أنتم حاضرون. Okay. Mrs. Sabah, are you ready in the class? Mrs. Sabah. Mrs. Sabah. Mrs. Sabah حاضر. أحسنتم. Yes. Mrs. Sarah, are you in the class?